Hi everyone, my name is Magdalena Stenius, and I'll be presenting a little bit about machine learning operations, or MLOPS, and its impact on the whole field of machine learning. So shortly about myself, you can find me on GitHub at Magda Poppins. I've been working as an engineer at Valohai since 2019. And at Valohai, we're working with machine learning operations tooling. So our mission is to accelerate AI adoption by building the best data science tools available for the teams. And at Valohai, my job has been implementing features such as the Bayesian hyperparameter optimization and, for example, spot instance or preemptive instance compute for machine learning. The agenda for this talk will be, I'll be first starting off talking a little bit about the evolution and impacts of DevOps on software engineering. And from there, I'll be drawing a bridge to how MLOps then extends those practices into the field of machine learning. And finally, I'll conclude by giving some future visions for MLOps and looking a little bit at what the field will be like in a few years. And feel free to stop me at any moment and ask questions and in the chat as well. So let's start off at DevOps. When you move kind of from the testing phase or from the proof of concept phase into actually having software in production, we all know that the criteria really change. So your code suddenly needs to have all this kind of fail-safe, reproducible properties that aren't necessarily there when you're still in the POC phase. You'll need some kind of system for moving through different environments, for example, from the development environment to staging and then on to production. And you also need some kind of system for moving between versions in production. So, for example, swapping when A/B testing between two different versions of the code. There's also a requirement for a rapid rollback when you're deploying something and it might go wrong, and you also have all these increased security requirements. So DevOps is the methodology for bringing together these development and operations processes, and basically the goal is to automate the different phases of this DevOps lifecycle. We're using, for example, CI/CD to increase the speed and quality assurance of the code. We would be using monitoring to increase the feedback and visibility, and also, for example, infrastructure as code to make the infrastructure really reproducible and consistent. If we look back in time to the 90s, DevOps looked very different, and the DevOps cycle consisted of basically some guy or gal going to the customer site, downloading the code on a floppy disk, having a discussion there, having a coffee with the customer, then again like driving home, modifying the code, again like uploading a new version on the disk, and then driving back to the customer site. And it was like a very like multi-phased process. Whereas if we look at DevOps today, we see there is this fluent cycle where all of these different phases are just automated. And when I mentioned the DevOps lifecycle, this is what I was talking about. So here you can see that these are the steps needed basically to develop and publish software projects. And the only step we can see that is not automated is the coding step. So the coding step is basically where the team has their code review policies, they have their code review tools, some kind of version control, for example, Git, some kind of remote repository, for example, in GitHub, and the team also sets some test coverage goals. Then we move into the automated phase. So the first step is the building phase, where you are building and creating these artifacts, for example, Docker images from your code. Then you're moving on to the testing phase, where some kind of test environment needs to be created, and there is a test configuration that will run your tests on the code. Moving on, we go to the release phase, where you would have the specified environments that you want to use for your release, and you would also have some kind of rollback strategy. Then we go to the configuration phase, where you probably have some kind of infrastructure as code, setting up the networking for your application and also data storage. And finally, we have the monitoring phase, where we have, for example, alerts set up, monitoring stuff like CPU usage and response time and stuff like that. So when we're talking about modern DevOps, one of the main themes that we have encountered in the past years has been virtualization. And virtualization basically means that you add an additional layer of hardware, operating system, and storage, and enable thus the app to run agnostic to the underlying system. So that the same code that can be run, for example, on my computer can also easily be run on somebody else's computer. And the method for this, when we're talking about operating system level virtualization, is using containers. Practically, this means using Docker containers. And those containers, again, are created using images, and the image being something, excuse me, an image being something that contains all ingredients that are needed to run that software. So the operating system, the compilers, and the software itself. Another need that arises from this containerization trend is the need for container orchestration. So we are managing multiple of these interconnected container workloads. And we meet questions such as, how do we start the different containers? How do they get each other's network addresses? And for example, how do they connect with their storage? And the answer to this is usually Kubernetes. So many teams are now moving in software engineering to use Kubernetes as their kind of container orchestration system. Because it has features such as load balancing, it is self-healing, so it will automatically replace those containers that have erred, and also that provides automatic rollout and rollback of services. When we get to this point where we have DevOps taken to the level of, for example, container orchestration, it really is its own specialty in itself. And that's why there has become this role of DevOps engineer, which is a bit different than the traditional full stack or front-end or back-end engineer. And the impact of this whole change has been that it has really sped up the development cycle. So it has become very much more rapid. The quality has really drastically improved due to replacing the human kind of erring element with automation. And there has also been a significant drop in maintenance cost due to this automatization. So if we now move on to look at MLOPS, the MLOPS cycle is again a little bit different from the DevOps cycle, because when we look at modern day DevOps, we see everything is tied together. There are so many good tools and processes that are already established that it's quite straightforward to set up a good DevOps system. But in the field of ML, it's again very different. There is still a lot of manual work. There are Excels, there are tweaking things on your own computer, and perhaps you would upload your model finally, for example, to some cloud provider, but there is still a lot going on that is also just very manual work of the data scientist. So ML development is slow. It is slower than traditional software engineering, and there are some reasons for that. One of the theories is that because we have these different roles of the data scientist and then the engineer, And those roles are very different. The data scientist has a more mathematical and more scientific approach, perhaps, to programming, whereas the engineers have a more thorough grasp of these engineering best practices and, for example, are very familiar with the DevOps practices such as version control or tests and stuff like that. And due to these roles being so different, the teams where there are primarily data scientists are kind of a little bit coming behind in these engineering practices. That would be more easy if it was a more mixed team. Another reason for slow ML development is the role of data in ML. So where in traditional software, you would have the code, which is the absolute source of truth. And as long as you have a snapshot of that code, you would have a reproducible result. But in ML, you have much more than just code. And this is a very often showed picture that illustrates just that. This is from an article by Google engineers called Hidden Technical Depth in Machine Learning Systems, published around a decade ago. And this specific image illustrates very well the kind of very small role of ML code actually in these machine learning projects and the vastness of the surrounding infrastructure in it. So when we look at this picture, we can really understand that when, for example, in traditional software, you have to worry about your version control of the code. You have to worry about like the monitoring of that application, the tests, deployment, and the CI/CD. And when we move to machine learning, it quickly grows to a much vaster domain. So you have your monitoring of your data, the versioning of data, perhaps, versioning also of the hyperparameters used. You might get some cyclical dependencies, which are not there in software projects. Then you also have to worry about the whole data area in your application and the data validation. And also the model quality evaluation or model monitoring is becomes a much bigger challenge than simply just monitoring the kind of quality of the software. So if we now try and look at an example of a machine learning pipeline, the first component would be the data engineering part, where the ETL and feature engineering are taking place. These are still kind of causing many companies huge troubles, and it's definitely a topic that will be more and more automated in the future. The next step is moving on to the training pipeline phase. So in the training pipeline, you would have the training and hyperparameter tuning. And this is not the experimentation phase. So this is training that's going on outside of the experimentation. In the training pipeline, you would also have the evaluation of the trained model metadata and therefore evaluation of the training results. And finally, after that evaluation phase, you have the serving node where you are making the model accessible to your users, for example, via some kind of inference endpoint or batch inference. And in the serving node, you would also have some kind of model monitoring and following setup. And what then is left outside of this automated pipeline is, as I said, the exploration phase. So similarly to software engineering, ML and data science is also a creative process. And in that creative process, there is the data scientist or ML engineer who is using their best knowledge to kind of find creative ways to make their model better and solve the challenges they have. And that's something that cannot be automated, as in software, you cannot automate the coding phase. So we were talking a little bit about the artifacts in DevOps. So that would be, for example, the snapshot of the code. But in an MLOPS system, the artifacts are not only the code itself, but also the data used for the training and the hyperparameters. And to be able to reproduce and explain a result in machine learning, you would need all of these to be versioned. This is also sometimes required by some officials if your model has something to do with perhaps making choices that need to be traceable and explainable later on. For example, I think debt or this bank loan systems are often kind of models that are needed to, where all of this is needed for later use if asked for by the officials. And as you know, I work for Valohai, and in Valohai, this is the example of how we trace these artifacts in every execution or in every model training. Sorry. So here we have a training run where we see the commit in the code where that training run was started from. We also see the inputs and their URLs, which can be versioned, for example, in the versioned S3 bucket. And then we have the parameters or hyperparameters, which are also saved. And in addition to that, you can also see the environment and the Docker image, which was used to produce this result, and the price of the run. So when we look at MLOps solutions for your team, then we probably start looking at the large cloud providers first, for example, Google Cloud or AWS. And SageMaker is something that pops up really often. So there are good sides and bad sides to these big proprietary solutions. The upside is definitely the ease of use. So there has been a very far abstraction, for example, in SageMaker, away from the Kubernetes, away from the Docker images, and into just a very sciencey lab. The downside then is the heavy vendor lock-in. So once you decide to move all of your ML on top of SageMaker, there's basically no going back. And also, if you have requirements for being on premise, if you have sensitive data that may not leave the premises, then this is also not an option. For some teams, there also might be kind of customization requirements that are not able to be met by these solutions due to the heavy abstraction in them. So depending a lot on what your team are looking for and what you need in that moment, this could be a solution for you, or it could there could be something else. One of the alternatives for this would be to basically build your own MLOps system. I see a lot of teams going down this path, but there are so many challenges when you start working with this. The primary one would be, if you're a small startup, you have a team of highly skilled data scientists, and you want them to create the MLOps infrastructure. There is this huge skill set mismatch between the ops side and the data scientists, whereas you don't want to force someone who is an artificial intelligence expert to work with Kubernetes. This will just be a very large waste of time, and it will cost some work happiness as well, because if you're a data scientist, you expect to be working with actual data science instead of being stuck with configuring Kubernetes and wondering why your pod is not starting. And there's also this kind of whole topic of, you can maybe craft one pipeline. If you're a small startup, you're just starting up, you don't want to invest in a solution yet, so you can maybe get your first pipeline built. The challenge comes then when scaling up and really moving from the one pipeline, one model system to having multiple production models. And it can be a big step to take if you're moving with your own MLOps system. So that was a little bit about the MLOps field as it is right now and what the themes are there. And now I'll want to take some glances at the future. So if we look at MLOPS solutions today, we have already used some cloud resources and accelerators in training. So that's already kind of everyday bread for data scientists working today. There are also automated deployments that are already going on and being used by teams. It's quite common to have distinct staging and production environments, or at least different like model swapping easily between these environments. Then there's some solutions for model monitoring. This is improving all the time. We have still a lot of manual work in the feature engineering and data processing, which causes like a bit of a slowdown. And it's one of the main challenges that teams are trying to solve today in MLOps infrastructure, kind of getting the data processing and the data phase in the MLOps pipeline to work smoother. There's also still a lot of manual model tweaking going on. So data scientists still aren't fully utilizing tools such as the automated hyperparameter optimization and such. And continuous integration, delivery, and training is also still kind of taking its shape. Teams are a little bit waiting for some easier solutions on how to work with this. So all of this is still kind of taking shape. And if we take a look at the future and what MLOps could be tomorrow, there would be at least one theme that I can see very heavily represented in different conferences and speeches is the feature stores and the utilization of kind of this feature abstraction layer that would kind of help with the whole data processing in the beginning of the model pipeline. There's also a rise in the automated retraining. So I think more and more teams are going to start looking into kind of having monitoring connected to automated retraining, and thus creating kind of a self-healing system. So in self-healing systems, the idea would be that you have monitoring set up to monitor, for example, the data drift or the model drift, and then an automated system to correct that and give feedback to the data part of the pipeline. If we look even further into the future, we could look at self-improving systems, not only systems reacting to monitoring in order to prevent damage and regression, but also systems that are kind of continuously looking for, training the models to become better and kind of finding even more optimal parameters and stuff like that. Also, one trend that could be seen is walking from manual feature engineering and this kind of heavy role of the features into instead having raw data and having just the model look at this vastness of raw data and learn from that without the human kind of having to take part in designing what part of that data is the part that we are learning from. There would also be probably a rise in using automated hyperparameter tuning. So, for example, Bayesian optimization. Twitter just had this big black box optimization challenge with which Valohay actually was also part of last year, where there were teams competing in this black box style where you're trying to optimize the hyperparameters without kind of having visibility into the actual models. So that's definitely a trend that's probably becoming more and more salient because that can really speed up the data scientists' work in finding the best parameters available. And another trend that could be seen is the training while consuming. So instead of basically having a model that is trained one time, you would have a model that is continuously retraining when it's consumed. So kind of using each input as a source for training. So if we want to assess the MLOps maturity of our system, then we at Valahai have provided this kind of 3-step model for MLOps maturity, where we have seen different teams kind of walking through the different steps of developing their MLOps solutions, or kind of getting into different patterns in their MLOps solutions. And what we see first is teams starting to get closer to ML, are in the data-centric step. So for them, the data preparation, the data engineering is like the main focus point. And the managing of this data is like a key problem. And these teams are usually looking to purchase, for example, data lakes, or trying to somehow get some kind of structure to manage this data solutions that they have. When teams are moving away from that step, when they got some order into their data, then they move into the model-centric step. So you have the data available, it's ready to use for ML, you have it prepared, and it is stored in some sensible way. Then you start using, for example, notebooks to achieve, the first models and the initial versions of models. And there's a lot of experimentation going on. You don't yet have production models, but you're very interested in kind of getting your first models out there. And these teams are looking for solutions that can help them deploy their models and kind of get the first models out there so that they could start seeing the value of them. And then when we move still further ahead, we can see the pipeline-centric teams, where basically you already have production ML and you have models out there that are proven valuable, but they need to be maintained. And basically at this phase, the teams are looking for tools to help them with this maintenance. So for example, retraining and the model tweaking, as well as the ease of onboarding new team members are what become central questions at this step. And that's when solutions such as Valahai come in, where we offer basically the whole pipeline as a product. So this model is based on a questionnaire from 2020, where we asked about 350 data scientists about what they're trying to accomplish during the next 3 months. And we can see how the distribution is kind of like a wave going towards the pipeline-centric step. So at the beginning, at the data-centric step, teams are looking to collect more data, figure out how data can be used, also learning about machine learning in general. And then as they mature, they go into this model-centric phase where they are developing the first models for production use, trying to deploy their first models, and trying to prove the potential of machine learning so that they could kind of get the funding to continue with this work. And then kind of the minority at the forefront are then looking already at these topics such as automated retraining and the production model monitoring. And if you're interested in looking more at this questionnaire and the report that is based on that, then you can find that on Valahai's page. So I notice I'm really ahead of my time, but here are some concluding remarks. The changes that MLOps will bring, the first change is definitely that it will speed up the model development and delivery iterations, as we have seen in DevOps. And that's going to actually have a huge impact on the whole ML scene, because right now machine learning development is quite expensive, it's quite tedious, and it's very much R&D. But when we get this speed up through and we actually make start creating the standards of MLOps, then teams can really reach a new level of speed in the model development. And this allows also kind of great solutions to be made by companies that wouldn't otherwise have the resources, or who are not yet in machine learning because of this kind of slowness and large cost. And when we were looking at a little bit at manual and automated processes, in DevOps, we still see that the coding processes, like actual software development process, the coding part is manual, but in machine learning, I believe that we can kind of automate the coding process even further. So this kind of will change the role of the data scientists. If we, for example, use this automated hyperparameter optimization, or if we start doing learning from raw data, or these models that aren't well, moving into more like deep learning and stuff like that, the data scientist's role kind of becomes more of an observer and understander, whereas the automation or the pipeline takes a more prominent role in the creation of the model. So this is kind of the last future vision that I have, that is the role of explainable AI and machine learning becoming more and more central, and data scientists basically being those who actually can do that explaining, can do that reasoning, and who can see the system as a whole and the different parts of it and how they're playing together. So yes, that's all I have for today. And perhaps there are some questions.
Thank you, Magda. So, yeah, I'm just making my first steps in the machine learning. So I was very excited to hear what it all, like how it all works in the production environments and production setups, and the future of the machine learning especially. Any questions, fellows? I'll probably warm up the question session by asking some. As far as I understand, the black box optimization task is very much complicated by the thing that you need to choose proper algorithms for the model, like proper approaches to learn on your data. And if it wasn't enough, you need to choose many parameters for these algorithms. So many of the things that you might want to optimize are not continuous. They are like changing, like by changing just one thing, you are changing dramatically the thing that you're trying to teach. So I can only imagine how much it costs to implement this black box optimization thing. Do you have anything in your, like, just to share about this?
Yes, so I can actually talk about, well, my own experience in implementing this Bayesian optimization on Valahai. So in Bayesian hyperparameter optimization, basically the Bayesian model will look at the kind of space of your hyperparameters and try to find the optimal kind of like tops or lows in that space. And for that, there is actually some different open source libraries that are already implementing the whole optimization phase. So for example, Optuna is one of those libraries that is widely used. Also HyperOpt is a similar kind of library where you basically give the library your the model outputs, and then it will kind of try to guess some next hyperparameters for you. Of course, this is also quite costly, so you would need kind of machines to then be able to test those out and run. It's kind of like running a random search for hyperparameters, but the guesses are just better. But it still needs a lot of compute power, of course.
Yeah, it is. I guess it's a little of trade-off between the cost of engineering, like human participation, and the cost of computers participation. And if engineering with like the mature guy or a girl sitting and understanding the data and understanding the outcomes of the experiments is something that's I guess, more predictable than the involvement of machine optimization, machine-driven optimization is sort of like brute force approach, right? So you just try everything and trying to find which one works better, right?
Yeah, I think the best use of like this automated like model improvement is when there's a data scientist who is an expert in their field and they can give the good starting values. And then from there, that small like tweak can be made perhaps to better. But yeah, of course, it's not like any random person could go there and guess any values, and then the model would just by this hyperparameter optimization become perfect. You need to kind of know what you're doing.
Absolutely. All right. Well, we still have some minutes. I don't want to start earlier because, there might be some people who count on like the next presentation starting on time. So probably have some interesting stories about your working experience with the machine learning to share, something funny or something we can all learn from.
Let's see. So yeah, I was working as a consultant before joining Valohai, and I was really interested in machine learning, and I got the opportunity to start at Valohai, but I wasn't really an expert in that field. And one of the first things that I actually got on my workplate was this Bayesian hyperparameter optimization service task. It was so much blood, sweat, and tears that went into that, and I guess the biggest pain is using these open source libraries, although they're like so useful and they're very. I'm very happy that they are maintained and that people are kind of supporting them and also contributing to them. But I have to say, like, those have been the lowest lows of my engineering career when I have had to had the happiness.
So true. There's definitely a learning curve to them.
Yeah, and for example, I have one of my star moments has been I have contributed some code to Jupyter Notebook, and that was really cool. But I actually realized when looking at the Jupyter Notebook code that there had been some class of students who had had a course project to contribute, I guess, to open source or to Jupyter Notebook, and it was like it didn't make any sense. Like their contribution were just like completely crazy. The commit messages were like really far out there. So this is also like one topic. If you're interested in open source and developing these tools, like there is no barrier. Anyone can do it, and you will get help. And Hacktoberfest is awesome for that because you will really get like help and support from the people working on those projects.
Oh yes, and by the way, contributing to open source is a good way to learn how the things work under the bonnet. Like until my first issue that I was like able to address. Like I'm a Python mainly developer, and there was like a huge path before I first opened the Python source code. And when I did this for the first time, it was such an epiphany to like look at the things working under the bonnet. So yeah, I can imagine people who like without any software development background, try to fix something for themselves. They probably find not working on. They think that it's not working correctly and contributing. And well, it's a matter of community behind the project to probably find out if it's good or bad, and probably filter out some wrong contributions from the releases.
Yeah.
But yeah. By the way, what kind of toolset do you use at your workspace? Is it still something like notebooks or Databricks or probably some Jupyter notebooks?
At my work. So I'm working basically with the engineering parts of Valohai. So we actually have a Jupyter notebook solution called JupyHi, which is a Jupyter integration. But we also, my work is mainly, I work with PyCharm. And for example, right now I'm working with the possibility to remotely debug your code. So basically when you're using Valohai, what you do is you have your machine learning code, your model, and you will upload that to Valohai, and then you can use any machine anywhere, Google Cloud or AWS or Azure to run it. And now we want to add the remote debugging possibility so that you could actually from your own computer debug the code as it's running in the cloud. So that's what I'm working with right now. Much infrastructure.
Yeah, so nice. Yeah, so you're basically also trying to, like, you're writing your tools for yourself, right? In Valohai. Respect. Yeah, this is one of the things I like about our profession. That, yeah, you can definitely do this sometimes when you like something.
And I think you can really see like the change in the whole programming scene. Like even if you're a web developer or something, that kind of there is this divergence of the people who are writing the tools and then the people who are using the tools. And I think like the tools are becoming better and better all the time. So like there are so many like ready-made web solutions already that kind of take away some of the work. So that's also why it's fun to work for a company that is actually like creating tools for developers, because then you're on the kind of more advanced side of engineering. So that's really
Indeed, yes.